today we're back on the computer, and Ho-Kei is going to tell us about columnar crystals. Over to you.
So thank you, Simon, and thanks Edu and Stefan for organizing this conference and inviting me to come to give a presentation of what I have been doing in the past 10 years or so. And then all this work started with collaboration with Dennis, Stefan, and Edu during my time as a postdoc in Trinity College Dublin, and more than 10 years ago. So this is a picture of a typical picture of what we do. To put it simply, we pack arc spheres into a cylindrical tube, and to be more specific, we pack arc spheres. But later on, in a second talk today by Jens, who is a co-author of a book we published earlier this year, we also talk about packings of soft spheres, also in cylindrical confinement. Yeah. So a bit about myself. I grew up in Hong Kong, and then afterwards I went to the University of Manchester to study a PhD, probably the same time as Edu. Yeah, we were in the same Schuster building. Yeah, but we just didn't meet at that time. Yeah, we met later in Dublin. Yeah. And afterwards, I also did a few postdocs, respectively in Hong Kong, in Dublin, and later in the UK. And afterwards, I took up a position as an associate professor in Shenzhen, China. So my research interests consist of the following areas. First one is packing problems, which I will be talking about today. But I'm also interested in electrostatics, and in particular, electrostatic interactions of charged horizontal particles, which might be related to packing problems in electrostatic systems. If any one of you are interested in my work in this area, please feel free to discuss with me in the afternoon. So first and foremost, I'd like to thank again for my collaborators and students over the years, Dennis, Stefan, and Edu, and also my collaborators in Shenzhen, China, Professor Zhong Zhen, he's the head of our School of Science, and also my former postdoc, Wei Jin, and also a couple of my postgraduate and undergraduate students. So I would like to thank my monograph co-author, Jens, who I'm lucky to meet in person today for the first time. So he will talk about the contents of our book in greater details. And of course, I'd like to thank the support from various grants that I have received over the years. So first, I'd like to maybe I'm not the right person to give a definition of what packing problems are, but here just some of my very brief views of what we mean by packing problems. So for me, I refer to packing problems as problems in which we look for optimal arrangements of objects in space, right? And I'm sure all of you have encountered such problems in various contexts. And from the physics point of view, I like to define packing problems as follows. We look for optimal arrangements of objects under a given set of constraints. These constraints can be the shapes and sizes of the objects concerned. And also, if we are talking about packings of particles in geometric confinement, then we will also need to specify the shapes and sizes of the container. And we also need to give a definition of what we mean by optimal. And in many cases, we refer to optimal as the highest density configurations, or in some cases, could be a minimal surface area configuration, or maybe it could be a random distribution or other definitions. And here I give you two very famous examples of packing problems. The first one is everyone of you would know. There's the densest arrangements of identical spheres in three-dimensional unbounded space, and this is known as the Kepler conjecture. And we all know that the FCC and the HCP are solutions to this problem, and it has taken more than 400 years for this to be proved mathematically by Professor Thomas Hales, who will be arriving here next week. And another famous example is the Kelvin problem, and we look for minimal surface arrangements. And glad to have Dennis here because he is an icon for this problem. He founded the Weyerfeld structure that give a counterexample to the original Kelvin conjecture. And we study packing problems. One reason is that we want to understand structures of matter. For example, if we consider the FCC and the HCP structures, then we can use this solution as models for the structures of a variety of solids. On the other hand, for random packings, we can also use such solutions to understand the structures of liquids. And this was first proposed by Brunel in the 1960s. And the topic I'm going to talk about today is also serves a similar purpose of understanding structures of matter. And we will talk about how particles inside cylindrical confinement obtain the densest packed states. So the very first paper that addresses these problems, and we have cited a lot, is the one by Pickett and his colleagues. It was published in PRL in the year 2000. Yeah. So they look for the densest packed structures of identical spheres in a cylindrical tube, and they use a method of simulated annealing to obtain such structures up to a certain diameter ratio between the confining cylinder and the confined particles. So here are a few snapshots of fruit packings. Actually, these packings I obtained. These pictures were taken by myself while I was on a trip to a hotel in Beijing. So obviously they were impressed by these packings, not only because of their interesting physics, but also because of their aesthetics values. And these are some other packings obtained by my students. I asked them to use ping pong balls to do some experiments on a sequential deposition on how to obtain these packings. So,
I can interrupt the questions.
Sorry.
Yesterday, I think just as you arrived, there were some. Maybe you brought them, but there were some sets of small balls and a cylindrical tube.
Yes, I've already taken pictures of that.
Yeah. So just the comment is that the question is that you didn't arrange those. You saw them. Someone arranged them with the left.
Yes, these are the sort of decorations I saw in there.
But arrange them carefully. We played around with them a little bit, but when it's there, it's very hard to get them to anneal into those patterns. They tend to make something much less helical.
Right.
So quite some care in setting them up. So I assume the ones that your students prepared, they took some care.
But yeah, I'm not sure they took a hard work on this. Yeah. So Pickett and his colleagues refers to this observation of chirality in such a systems as spontaneous chirality, which I will address in the later parts of my talk. Yeah. So when I arrived at Dublin in around autumn of 2009, I also did a bit of experiments of hard spheres inside a cylindrical tube. So these are pictures this is one of the pictures I took with respect to my hard sphere experiments. So at that time, I found that these structures, in some cases, not in all cases, can be obtained simply by just dropping the spheres one by one into their lowest possible position, which I later on will refer to as a method of sequential deposition. So this is another picture of me playing around with columnar structures of forms. So, so as I mentioned before, we study this sort of problems. One of the reasons is that we want to understand some structures of matters. So here are the sort of various types of experimental systems that, in which such columnar structures have been obtained. Just a few examples. In the micro scale, we have the colloidal crystal wires and this and confined microbubbles. This work was published by Stefan and his group and by Aaron. And I think they use a X-ray tomography to obtain these structures, if I remember correctly.
Yes.
And here we've also got a few examples at the nanoscales. So one prominent example is the packings of fullerenes inside nanotubes, where people have also observed structures that are very similar to those of hard sphere packings. So here is a snapshot of what have been done in the past decade or so regarding this problem. I mean, theoretically. So this is the paper I just mentioned, the paper by Pickett in year 2000, and in year 2011. I was in Dublin, so myself, Dennis, and Edu, the three of us, worked on this problem, and we extended this problem to values of to higher values of the diameter ratio D between the confining cylinder and the confined spheres. So what we've done is twofold. First, we use simulator annealing to obtain these structures. And secondly, we propose an analytic theory to account for the existence of helical structures, or the so-called line slip structures, in certain values of the diameter ratio. And in the same year, I myself, based on my experiments on the hard spheres packings, and I proposed a method of sequential deposition to obtain these packings experimentally and computationally. And a few years later, the group by Professor Patrick Charbonneau in Duke University, they used another computational method to obtain packings at much larger diameter ratios, up to around 4. So overall speaking, for this particular problem, in most cases, there only exists numerical solutions. Yeah. But for us, I think that analytic solutions are best. Are best for any structural. Sorry,
Just for clarification, when you say solution, you mean a lowest energy state?
Densest packed densest packed, yeah. So, and in most cases, it corresponds to a lowest energy state. Yeah. So, but for any structural analysis, for us, I think that analytic solutions are the best, ideal, because they would allow us to determine accurately whether any pair of neighboring spheres are in mutual contact. Because in some cases, two spheres, if you consider the numerical solutions, they could be too close. Then the separation, you don't know whether they are real separations or whether they fall within the realm of numerical errors. Yeah. So, yeah. However, in most cases, analytic solutions are elusive. So here is an overview of of the results obtained by pickers. Yeah. So by simulated annealing, they have obtained a variety of structures. As the diameter ratio increases from 1, which corresponds to the simple linear chain structure, and we will have the planar zigzag structure. And if this diameter ratio goes past a critical value of around 1.866, which actually corresponds to an analytic value of 1 plus √3/2, yeah, then you will have the emergence of the first helical structures, and we refer to this structure as a single helix structures. And if you continue to increase the diameter ratio, you will get a variety of helical or chiral structures, which contain the double helix structures and triple helix structures, and so on. Yeah. However, at certain singular values of these diameter ratios, we will have some achiral structures. For example, if this ratio is at the exact value of 2, then you will have an achiral structure where you have 2 spheres lying on the same vertical separation. And then if you move a bit further, you will also have another pair of spheres lying on the same vertical position. But then this pair of spheres has a 90-degree rotation with the previous one, and so on. So one of the physical problem we want to address is why do we, in some cases, have the emergence of chiral structures, and why in some particular values of this diameter ratio, we have this sort of symmetric or achiral structures. This is the problem we want to understand. So in 2011, Dennis and Edu and myself addressed this problem by proposing an analytic theory. So, but this theory was based on an observation that the numerically obtained structures up to around 2.7 something, right? The densest structures have all the spheres in touch with the wall of the confining cylinder. So in this case, we can simplify the problem, the 3-dimensional problem, into a 2-dimensional one. Why? Because if you have a side view of this system, then you can consider an inner imaginary cylindrical wall in which all the sphere centers are embedded, right? And in this case, if you think of a process of unrolling this surface, then it becomes a 2-dimensional problem, right? But this problem has a particular periodicity constraint. That is, this periodicity corresponds to one circumference of the structures. That means going along this periodicity and we'll end up with the same sphere that you originally started, right? So based on this periodicity constraint, we propose that if the corresponding diameter ratio does not meet certain values, then this densest packing of spheres have to adjust themselves in order to have this periodicity fulfilled, right? And I also like to mention that if you look at this surface pattern, you may think of it as a related problem of disk packings. So think of each particles on this surface as a circular disk or this enlarged, elongated in certain directions. Yeah, and think of it as trying to pack themselves as densely as possible. So if we don't have this periodicity constraint, we will expect a hexagonal close packing, right? But if we want but it needs to fulfill this periodicity requirement, then it will need to adjust themselves. There are several ways to adjust it, but we found numerically that one of the best ways is to keep certain areas to be densest packed. That is, keep certain areas to be in their hexagonal post-packed states. But between these areas, you can have some sort of shear or sliding. Sliding until the periodicity requirement is fulfilled. So this is how the so-called helical structures or line slip structures emerge. So this is the key ideas. So I guess if we want to discuss the details of this theory, we can have such discussions during the free time with probably with Edu and Dennis and myself. So next, I'd like to talk about how these structures can be constructed experimentally or computationally via a relatively simple method of sequential deposition. By sequential deposition, I just mean dropping the spheres one by one onto the lowest possible positions. So here we consider a very simple example, the planar zigzag structure, right? So if we start off with a very first sphere at the bottom, then you want to place the second sphere, and then naturally the second sphere in its lowest possible position would be at an angular separation of pi from the first sphere, right? And the third one is the same, as an angular separation of pi from the second sphere and so on. And this makes up a planar zigzag structure, right? So this is a very simple example, right? So by doing so, we are achieving a local maximization of the packing factor. Because if you think of it, if you put the second sphere in its lowest possible position, then this region has already obtained its highest density, right? However, this is not the end of the story, because in some cases we can also fine-tune or adjust the configurations of the few spheres at the bottom to achieve an even denser structure, right? Why? Because if you think it this way, if you adjust the position of the second sphere, if you pick it up from this lowest possible position, then of course the vertical separation between the first and the second spheres has to be sacrificed, right? In terms of lowest and in terms of densest packing there. But this will cater more space for the third sphere to be placed at a lower position. So in doing so, we are actually increasing or maximizing the local density of a configuration that consists of the first three spheres. I will go into greater details later. Yeah. So, so in doing so, we have not only achieved densest packed structures that look very, very similar to those obtained by Edu through simulated annealing, but we have also discovered from some novel order structures that were not expected at all. So this is an illustration of how we can obtain such a sort of a globally densest structures. So we sacrifice the lowest position of the second sphere and allow the third sphere to be placed at a lower position. So this is one example of the novel structures discovered during this process of tuning the template. So for example, here we have a so-called hybrid helix structures. I didn't know how to call it, so I just at that time I just referred to it as a hybrid helix structure, because this structure you can see that it consists of two helices packed densely with each other. but then you have a single helix neighboring to this pair of helices. So and it corresponds to one of the local peaks of the packing fraction if you adjust the angular position of the second sphere. So a few years later, I have also studied the two helical structures at the diameter ratios smaller than 2 analytically. So we have obtained analytic solutions for these two structures, and that was published in AIP Advances. But I would also like to mention that this year we have also obtained a national patent for the analytic solutions to these two structures. Of course, it's a patent in China. It has nothing to do with applications in Europe or whatever.
So China is not limited to the rest of the
Yes. So the idea is that we thought of each of these two structures as a repetition of microstructures, and each microstructure consists of a triplet of spheres, right? And we found that the single helix structure can be thought of as a repetition of the same microstructure, and the double helix structure is an alternation between two different microstructures. And this is the optimization mechanism that I mentioned just now. And if you plot the vertical separation between any pair of adjacent spheres, you will find that in a single helix regime, it's only a single value because it's a single helix structure. Right? But you observe you have a bifurcation of this delta Z, the vertical separation or the angular separation in the double helix structures. And we have also studied the physical properties of these structures. And 2 years ago, we looked at the electrical conductivity of these structures analytically, and we found that the conductivity generally decreases for increasing diameter ratio. The reason is that as you increase the diameter ratio, the spheres or the equivalent resistors are packed more densely. Yeah, and this increases the resistivity and hence decreases the corresponding conductivity. Yeah, but then there is an abrupt increase of the conductivity at the structural at two of the structural transitions. That's because there's an increase in interparticle contacts at the structural and these transitions. So I also like to mention a bit the work by the group of Patrick Charbonneau. So they have used another method to study this problem of diameter ratios up to around 4. And they have discovered a total of 17 columnar structures with so-called internal spheres. So this was beyond the realm of the work that I mentioned just now. Because we've got internal spheres, so we need some more complicated methods to analyze the structures. I think you, Edu and Sever, you have later analyzed some of these structures, multi-layer structures, right?
We published some of the structures of the internal spheres.
Internal spheres, right?
And we broke them up and so on. And then Charbonneau came later and he said that he found that some of our structures were not the densest. So he beat us in that.
Okay. I'm sorry about that.
Okay. I can live with it.
Oh, okay. So I guess we have to work hard again to beat them again. Right. So anyway, so one of the ideas was to consider these structures as their name suggested, they are multi-layer structures, right? One of the ideas is to sort of decouple the different layers in such structures and analyze them separately. But this idea, I don't know how far it has gone for now. Yeah, so I won't go into details now. And so in recent years, we have myself and my postdoc and my collaborator in Shenzhen, we have we got a big board with spheres. Yeah, they are too simple. So we move on to shape-anisotropic particles, and we use Monte Carlo simulations to obtain a variety of densest-packed structures of hard spheroids in cylindrical confinement. So for such systems, we not only consider the so-called diameter ratio, which corresponds to in this case corresponds to the ratio between the confining cylinder and the short axis of each of such particles. We also consider the shape and isotropy of each particle, which is defined as a ratio between the long axis and the short axis. So we have obtained a total of at least 7 types of structures, and we've got single heat structures, double heat structures, and triple heat structures. So these are sort of expected because in the inference, under the inference of the confining cylinder, we expect helicity to emerge, as in the case of sphere packings, because of the periodicity requirement that I mentioned just now. But here we've also got some novel structures. They are not helical, but they have specific particle orientations. For example, we have this so-called unidirectional zigzag structures, where all the particles are oriented in the same direction. And in some cases, we've also got a bidirectional crystal structures, where you have it's a bit like the achirodopics in the case of sphere packings. But here we've got 2 particles oriented in the same directions, and then followed by another pair of particles in another direction, which is roughly 90 degrees rotation from the previous pair. And in some cases, we have also obtained achirodopics and achirotriplets, as in the case of sphere packings.
Can I generally ask, when you have achiral structures, so the whichever measure of chirality you're using is 0, right? Are these isolated in parameter space, or are there intervals in parameter space?
Good question. I'll show you in a minute the corresponding phase diagram. So this is the sort of phase diagram. I actually should not use the term phase diagram, because one of the referees said that it's not, they are not phases. So right now I would just like to say that they are diagrams of densest-packed.
I think you can call it whatever you want. That's the referees of the audience. So. In which case we'll have them forcibly ejected.
So a serious question. Are these ellipsoids, or are you allowing non-centrally symmetric spheroids like eggs, for example?
They're all, I mean, they are all spheroids.
Yeah, but in the ellipsoids, so essentially symmetric, invariant under x goes to minus x.
Yes.
So essentially you want eggs, because eggs are probably even more interesting.
Okay, yeah, thank you. So so we have studied cases of oblates, which means that and also prolates. Prolates are the elongated ones, and the oblates are the compressed ones. And here is a diagram that shows at which parameters that each structure has been obtained. So here we've got a rather broad area for the existence of the unidirectional zigzag structure. So here I would like to also mention that this white dashed lines correspond to the case of sphere packings, right? So these results are in agreement with those of sphere packings. And we've got these two areas of single helix structures. And here we've got two types of single helix structures. Why? Because apart from the helicity of the structures, we also have to consider the orientations of the particles. So one type corresponds to the to opposite helicities between particles orientations and particles positions, and the other type corresponds to the same helicity between the particles orientations and particles positions. So what does it mean? If we consider sort of the same helicity, it means that if we have a, let's say, for example, this is the long axis of one of these particles. Same helicity means that the particles orientations goes as the same way as the helicity of the whole structures, and opposite means is opposite. I don't go into the details. And we've also got areas of double helix structures and triple helix structures and so on. And for the achiral doublets and the achiral triplets. So this goes back to a question by Sasha. And for the case of sphere packings, we know that the achiral doublets only occur at a single value of b equal to 2, right? But in the case of sphere packing, here you can see that the achiral doublets occurs over finite range in the diagram. So this is a plot of the corresponding packing fractions. I won't go into details right now, but for this one, I'd like to talk about it in details. So one of the problems we want to address is why do these structures emerge as they are? And here we can consider an example for the transition from the single helix structures to the unidirectional zigzag structures. And such transitions, you can see that such transitions occurs as you increases the shape and isotropy of the particles. That is, if you continue to elongate the particles, and you observe such a transition. So here we propose a mechanism for such transitions. By the way, these transitions are here referred to as continuous transitions because there is only one single structure existing at the corresponding transition point.
Can I ask quickly about this? Have you really done this as an experiment? Like manipulated the shape of the particles in real time?
These are all numerical results. Yeah. But
even in numerics,
yeah,
if you could change the aspect ratio of
Right.
particles during the simulation and actually see if dynamically they will rearrange rather than just running different simulations with different aspect ratio and otherwise.
we haven't done that yet, but I think this is a very good suggestion. Yeah, because we just changed. These structures were obtained independently by setting the corresponding parameter values. Yeah, but I agree that this would be a very good suggestions. I would expect that for hard particles, it might not have too much to do with the history of your dynamical process, but I'm not sure about soft particles, which I guess Jens will talk more about it, because there could be all sorts of hysteresis and effects in the case of the soft particles. Anyway, to understand what's going on, we consider this example. First, we consider a critical value. I call it AC of this anisotropy parameter A. And if this anisotropy is small enough, then each particle only has has a single contact point with the confining cylinder. Yeah. And that means that, the corresponding densest packings would be very similar to those of identical spheres, right? Because in this case, the dominant effects on the structures obtained would still be the effects from the confining cylindrical wall, right? And this is and the particle shape doesn't matter too much. And this also explains why in the one of the very first pictures I showed you about the fruit packings, it doesn't matter whether you are packing oranges or apples or lemons. Yeah, you will still get these helical packings, right? But if you further elongate these particles, you will reach a point where each particle is no longer has a single contact with the confining cylinder, but it has to be consist of two contact points. Yeah, if they are long enough. Yeah, but in this region, we still have sort of helical structures, because in this regime, the effects of the confining cylindrical wall are still dominant, right? But if you further elongate the particles, you will achieve a structural transition where the particles are just too long. Yeah, they are too long that they can no longer be the densest packed structures can no longer be just determined by the curvature of the cylindrical wall. So they will have to realign themselves in a uniform direction, uniform orientation, as shown in this picture. Yeah. So this is our understanding of this sort of a transition as you change the shape and isotropy of the particles. After getting done with this three-dimensional packings of shape and isotropic particles, we move on to a two-dimensional version of this problem. So at that time, we have still got. Am I overrun?
5 minutes.
5 minutes. Okay, I'll try my best. Okay, so we move to cases of two-dimensional packings of particles in quasi-one-dimensional confinement. So initially, we took a look at how the circular discs are packed inside such settings. So, but we found that this problem has already been done by someone else. That was done 30 years ago by a mathematician. So he proved that for such packings, the corresponding packing factor goes in this way. There is an oscillation of this packing factor, which looks a bit similar to the ones we observed for sphere packings. So the physics goes like this. It's very similar to the case of sphere packings, because at certain ratios between the confining channel and the confined particles, the particles can obtain their densest hexagonal close packed structures without the need to adjust themselves to the corresponding periodicity or the width of the system. But in other cases, they will have to adjust themselves in this way. So you can see that there are still regions of hexagonal close packings, but they have to slide against each other to achieve the corresponding periodicity constraint. So this explains why we have this oscillation of the packing fraction. And so we looked at shape-anisotropic and shape-anisotropy effects in such systems. So we carry out multi-color simulations for ellipses in such systems and make a comparison with results for cases of dense packings. And we found that in all the cases we have studied that the densest packings of hard ellipses inside a parallel strip are all affine transformations of some of the densest packings of this inside a parallel strip. And here we can classify such.
This is why I asked about the non-central symmetrical, the eggs,
Eggs, okay.
because it's not in this study. The eggs aren't.
Eggs, yeah, not they're not eggs, yeah. Yes. At least they are not chicken eggs.
Yes, they're
Okay. And we have classified such packings into 3 types. And if you remember from my previous slides that there are local maxima for the densest packings of this, yeah. And we refer to these local maximum structures as M structures. And these affine transformations can be classified into 3 types. One type refer to affine stretches of these M structures in whatever direction, right? And the other 2 types just correspond to affine stretches along the X directions and Y directions respectively. So here is a so-called diagram. I wouldn't call it phase diagram, okay? because the probably it's the same referee raised the same criticism. Yeah. So here's a diagram. Yeah. So as you see, as anisotropy parameter A increases, and so in most cases, the densest structures are just the M structures. They are just affine structures of the locally densest structures of these packings along particular directions. Yeah. And we want to, and we ask this question: why are all the ellipses of a densest structure along the same direction? And our answer was that we can think of these structures if think of the sort of the grain boundaries between regions of particles of different orientations. And we performed a bit of calculations of several types of structures that consist of varying numbers of these grain boundaries. And we found that there's a general trend, decreasing trend of the packing fraction as the number of grain boundaries increases. And the reason is very simple, because grain boundaries, they are not favorable in terms of densest packings. They create extra volume in the system. Yeah. So that explains why it's ideal to have all the particles aligned along the same direction, because it will minimize the number of grain boundaries and hence free volumes in the system. And almost finally, semi-finally, I also like to talk a bit about another work that I performed, that I carried out with one of my master's students. It was published last year. We have worked on identical particles, and we have worked on shape and isotropic particles. Yeah, but we haven't really worked on bidispersed or in general polydispersed particle. Yeah, because in the beginning we thought it's just too complicated, because for for example, for identical spheres, we've got one parameter. And then for identical spheroids, we've got two parameters. Then we thought that if we work on bi-dispersed particles, then we will have too many parameters to work on, right? But then we came up with this idea of working on a relatively simple system, but with poly-dispersed particles. This simple system corresponds to a regime where all the particles, all the structures are in the zigzag regime. Okay, and we found that the densest packed solution of such system, only in the zigzag regime, is a sort of a size-graded structure, in which the larger a particle, the closer it is located to either end of the system. That means it is some sort of an encapsulated structure where the smallest particles are encapsulated by the larger ones.
So when you say either in the system, you have hard walls,
Yes, but these are all hard particles and hard walls. Yeah.
the hard wall on either side.
Yes, yes. I know you may think about possible connections to biological systems where in those systems we have to deal with soft boundaries or soft particles. Yeah. But for the moment it's only a very simple system of hard particles and hard boundaries, right?
The top and the bottom,
Huh?
top and bottom, periodic.
Top in the bottom.
That's what I meant. Is that hard wall at the top and the hard wall at the bottom?
Oh, you mean top and bottom?
Yeah.
It doesn't matter.
It could be periodic on both sides.
No, sorry. Because here we are only dealing with finite number of particles.
You're saying it's always an ABCBA, it's like that.
Yes, yeah. We are only dealing with finite number of particles. Yes, and here we are
You're asking about the boundary conditions. So I know there are walls on the left and right.
Yes.
This can't go beyond, but if I go up and down the channel,
Yeah.
if I go right to the top, will I hit a hard wall? And if I go right to the bottom, will I hit?
There's also you may think of it as also a hard wall.
Okay.
Yeah, and for such systems where we define the densest packings, because we are dealing with a finite number of particles, we simply define the densest packings as the one with the smallest total length. Yeah, the shortest, the shortest.
And is this a statement about any polydispersed size distribution between, with sizes between 1 and 1/2, because that's what they have to be, right?
Yes.
So any distribution.
Yes, just for this particular type of system.
For the zigzag. Yeah.
For the zigzag. I don't know about the other types. That would be too complicated for now. Yeah. So we obtain these results both numerically and also analytically. But by analytical, I mean that we just propose a condition that can provide that can yield such densest packings. And the condition goes like this. I haven't put into the PPT, but I can explain a little bit. Because if you consider such a systems, if we found that analytically that if you consider the particles at either end, then if you have for example, if you have a smaller particle at either end of the system, then there is always a possibility of decreasing the total length of the system by swapping the two at the end. Yeah. So here we propose that by putting the largest particles at either end of the systems, there's no more possibility for such a swapping to decrease the corresponding total length. Yes. We can go into details, but one more minute.
Okay.
Yeah. So we have also I mean, these structures are too complicated, so we have also done a bit of 3D printing to visualize the structures, and we have tried upon two possible techniques to visualize such structures. So here a bit of summary, 30 seconds. Identical spheres in cylindrical confinement exhibit a great variety of densest-packed columnar structures, and they can serve as spherical models for the structures of a variety of physical systems at both the micro and the nano scale. And we have also worked on identical spheroids, and thanks to the additional rotational degrees of freedom, we have discovered a variety of structures with non-trivial orientational order. But on the contrary, identical ellipses inside a parallel strip exhibit only 3 types of densest-packed columnar structures as corresponding to the affine transformations of particular densest-packed structures of circular disk. The possible reason is that the geometric constraint exerting on these systems from 3-dimensional compressed to 2-dimensional system, limits the corresponding degrees of freedom, and therefore we only have such a relatively simple variety of structures obtained. So 15 seconds more. So for this topic, we want to raise the following key scientific questions. For identical spheres in cylindrical confinement, we want to ask, how do the densest packed structures approach the bulk cases of FCC or HCD structures as the diameter ratio D approaches infinity? I know that we can do this computationally, but we can not only rely on computational methods, because it will be very computational heavy task. So I wonder if there could be any theoretical approach to this problem. And for identical spheres in cylindrical confinement, in some cases, for structures with internal spheres, internal spheres are packed in a denser manner than the cylinder touching spheres. But in some other cases, the converse is true. We want to understand the mechanism of competition for space between these two types of spheres. And for the case of spheroids, there generally exists a competition between confinement-induced chiral ordering, which led to the helical structures we have observed, and the so-called shape-anisotropic induced orientational ordering. For example, the ones with all the particles aligned in the same direction. So we want to understand what are the factors that determine the winner between these two types of ordering. So one final question for the audience is that, so we have worked on all these columnar structures theoretically, especially for the experimentalists. Can we apply these results to the design and synthesis of chiral rod-like liquid crystal molecules or other types of materials or metal materials? So it's a list of publications in collaboration with Adil, Stefan, and Dennis. And thank you for your attention. Sorry for a bit overrun.
Any questions? Go on, Rob.
I want to go back to Anne's.
Okay, possible. Whenever we considered doing a study of spheroidal particles,
Yes.
we were inhibited by the fact that we weren't able to invent or find a good algorithm for contact or overlap.
Okay.
Can you say something about how you do that in practical terms, computationally?
Computationally, yes. So we have actually adopted a computational algorithm from Torquado's method. You say Professor Sal Torquado's method. Yeah, it was there was a method to to determine accurately the
Establish.
the contact condition. Yeah. We can.
Are you using a modern library routine, or did you invent that criterion computationally for doing that?
No. We just adopted that approach to deal with this problem. Of course,
Maybe we can talk
we
about
can talk about
later.
it.
It's a big
Yeah,
thing.
I think for the thesis, we have a certain what is it called acceptance.
Yeah.
To determine whether the particles are overlapping or in contact. Yeah. Okay. Thank you. Yeah.
Yes, I want to come back perhaps partway and then further back. So with already work, we want with discs, there's things that are proven. For ellipsoids, there are theorems like theorems of phase compensation.
Right.
Affine would be shear to get ellipsoids.
Right.
Are those theorems of these experimental results that you get? And these are the packing result. Yeah, I mean, I understand this. For example, this intuition for why you have all the little, no grain boundary that's possible.
Right.
Is that a theorem? Is that a experimental result? I'm just wondering. It's an interesting principle. But
Okay. I think it's for the moment is only an experimental.
So the reason I was asking about non-centrally symmetric ones, eggs, if you want, in 2 dimensions.
Yeah.
There, I think you've got interesting experiments, numerical experiments.
Right.
That's what I'm suggesting. Presumably this is what happens.
Okay.
It's a new phenomenon might have emerged.
Okay.
Just did a disc cave,
Okay.
egg-shaped disc, not centrally symmetric.
Okay. Yeah, I think my postdoc Wei Jinha as he's now a postdoc in Corey's group. I think he has and in his previous projects he has also worked on these egg-like structures.
Can I ask one other thing about your columns?
Called
Your columns, you're going to have the minimum height columns, the densest columns.
Yeah.
Versus
Yeah.
discs.
Yeah.
So it's conceivable that that's the right thing. But I just want to make sure I understand the principle, because I thought maybe a different principle held. You want to have different sizes put next to each other to get it shorter and shorter.
Yes.
I'm just surprised you don't choose a different sequence. You sure that's the best way to shorten them? Just wondering if you thought carefully about that. Not saying I know a different answer, just a little bit skeptical if that's the way to do it.
What do you mean by a different sequence?
Well, you say it's 80s. Well, actually, there's that third one. I didn't see the color yet. It's very a little hard to distinguish with my glasses on. I can see you've got ABCD, CBA.
Yeah.
So you're lining up. You have a large number of different transitions.
Yes.
I'm just surprised that more transitions don't do better.
Well, actually, it goes like, of course, of course, if you sort of invert it, then it's actually the same structure.
Sure.
Yeah.
But have you tried all possibilities?
Yes. Yeah.
Combinatorially?
Computationally, yeah.
Combinatorially?
Yes.
I have a related question. Does this have a well-defined continuum limit in the sense that I have a continuous size distribution with sizes between 1/2 and 1, and there is then a well-defined largest density of packing that results from this kind of ordered zigzag?
I think that's a very good question. Right now we have only tried finite size system, but of course we can try to extend sort of numerically to n towards infinity.
That would be very interesting.
That would be very interesting. But I have to stress that this result only works for the very limited regime of zigzag structures. Yeah, we haven't tried other scenarios before.
Before we break the coffee and before we think, okay, adios, if you have announcements to make.
Yeah, so, I think there's several different plans for what to do tonight. So, one plan is for people who want to go to see Brastock. So if there's anybody who wants to see Brastock, I'll put up a thing on the blackboard that you can just put your name underneath it. And we'll see if we can do about organizing tickets in that sense. There's some other people who might want to come out for a barbecue tonight, so I'll put out a barbecue. You want to come up and barbecue on the beach, we can organize that. And I think there's also a plan to go to see gypsy jazz music in town. But barbecue and gypsy jazz are not mutually exclusive, so we can do both if we want to. Okay.
Okay, so we'll return at 2012. Thanks for again.
Oh, yeah, thank you very much.